time talking about PIM, how it manifests, how it's measured, and discuss the differences between PIM testing and PIM Detect. And then we'll jump into using talking about using the automated PIM detection feature that's in the analyzer. Go over what the agenda is, which essentially is we'll talk about what passive intermodulation is. We'll define it. Then we'll talk about the various PIM sources and impact on base stations, and then we'll look at PIM testing overview. I think what we call PIM Detect is distinctly different from PIM testing in a number of ways, so I just want to make sure you understand that. Both PIM testing and PIM detection have their own strengths and weaknesses, and so this hopefully that'll give you an idea of where you want to use one versus the other. And then we'll specifically talk about the PIM Detect feature that's built into the analyzer. Let's spend some time talking about what is PIM. So there's a term called intermodulation distortion, and passive intermodulation really is a special case of intermodulation distortion. They're very similar in how they manifest themselves, but the source is a little bit different, so we'll talk about that. But basically, intermodulation distortion occurs when two or more signals that are coming into a device are at different frequencies, and they get combined inside the system. And if that system is nonlinear or exhibits nonlinear behavior, you end up with signals that weren't present at the input being generated inside the device itself. And so that's referred to as a nonlinear response. In other words, what goes in doesn't come out. Ideally, in some devices, you want intermodulation distortion. So for example, spectrum analyzers and radios and all kinds of other devices use this intermodulation distortion to their advantage. Just to give you an example, I'll just draw a quick diagram here. So for example, if you're trying to demodulate a radio signal, you can't hear at RF frequencies, right? You hear at audio frequencies. So what happens is the signal comes into a device. So let's say this is just a signal that's being transmitted, and that signal is at some frequency, and we'll just call it F, frequency F. That gets stuck into a device, and that device might be a mixer, for example, which looks like, if you look at a schematic, looks like a circle with an X in it. And what the mixer does is it inserts into that mixer another signal at a different frequency, and those two then produce intermodulation distortion in the mixer. And so what you have is two signals at different frequencies mix, and maybe I better call this one F1 and this one F2. Those two signals actually mix, F1 and F2, and out the other end, you end up with F1 and F2, but you also end up with these intermodulation distortion artifacts below and above those two signals that were input to the mixer. Well, that signal below is now at a lower frequency, and it can be demodulated and pumped out to audio. So a mixer really is used in an AM demodulator to give you that artifact so that you can actually then demodulate it and hear it. So all kinds of devices create intermodulation distortion. The problem is, in your devices, antenna systems, you don't want that, right? You want what goes in to be what comes out. So intermodulation distortion is good, can be used to advantage for some things, but it's not good when you're talking about your antennas. So here's another picture of the same thing I just drew. So signals are injected into a device, and this device, if it's nonlinear, produces these other signals that appear above and below the original signals. And so that's referred to as nonlinear. And what went in is not the only thing that's coming out. Hopefully that makes sense. There's all kinds of mechanisms for producing these nonlinear responses. Oops, a little too soon there. Either intended or unintended. So in a AMD modulator, you intend to do this. You intend to have these other frequency components produced by a nonlinear device. But in an antenna system, you don't intend that to happen, and you don't want that to happen. If you look at the original signals that are sitting at F1 and F2, you'll notice on this chart, so those are some distance apart in frequency terms, and that distance D is simply represented right here by subtracting F2 from F1. That's really the distance D below. And so if you factor out this equation, you end up saying that, okay, well, these signals F3 and F4, they can be represented by this formula. But really, it's just, all this formula really represents is that you have an artifact below and an artifact above the original signals. So PIM, how is it different from intermodulation distortion? Well, PIM is a special case of intermodulation distortion where intermodulation distortion is typically referred to in active devices. So for instance, like in an AMD modulator, transistors or diodes or whatever, those devices are usually powered, not always, but usually powered. The old crystal sets would do demodulation with just a passive crystal. So those weren't active, but many of the devices that create intermodulation distortion are active. Well, PIM is a special case of intermodulation distortion where there's no external power applied to the device. So the device is really passive, and the power that comes from the system is coming from the RF that's injected originally. So where you have an antenna system, the actual power that produces those intermods, the intermods in the last slide, F3 and F4, the power to produce those signals at F3 and F4 actually come from the original RF power itself. So it's the power present in the RF that gets used to create those unwanted signals. It's not an external power supply. So it's generally referred to as passive intermodulation. All right, well, let's talk about the impact on base stations. So common causes of PIM in a base station are probably most often just poor workmanship on connectors, but other things can create PIM. For example, connectors are out there for years and they eventually get corroded. If something's assembled with a little bit of debris or dirt or metal shavings in the RF path, that can create PIM as well. Another real common problem is incorrect connector torque. Those connectors are designed and have to be torqued within specifications or they'll produce PIM. PIM can actually be produced outside of an antenna, so if you have metallic or especially bimetal kinds of objects outside the antenna, that will produce PIM and actually go back into the antenna down the receive path. And I've done an awful lot of PIM testing in the past, and so I've seen things like mechanical failures, broken solder joints. Those aren't the norm, but they also can contribute to PIM. Connectors that get stressed, in other words, the bends right outside the connector are too sharp, and that can create problems. And then, one thing that was, especially when PIM was first being addressed, this is maybe 5 years ago, when people were really saying we got to address PIM, and PIM testers were all the rage and all that stuff. There's an awful lot of parts that were used in systems that really weren't designed properly. So anyway, one common thing that I saw was, let's say that this is that you've got a conductor, maybe a line that's coming through a device, and it's got a center conductor, say this line at the bottom, and then there's a shield outside the conductor. Well, oftentimes those shields are metal plated, so you might have a real thin coating of metal plate on that shield, and I'll exaggerate that here. So this area in here is actually a metal plate, maybe silver or some highly conductive material on a block of aluminum as the signal goes through next to that. And if that metal plate is too thin, you end up having some of the signal go through the plate. The opposite. If I've got a positive on the line here, I'm going to end up with negatives over here, or I'm going to end up with electrons moving back and forth through both of these. And if the shielding is too thin, you end up with electrons getting into the, say it's aluminum, and then you have electrons inside the silver, for example. And so that bimetal traverse of the electrons causes those electrons to move at different speeds through that material and create artifacts. So, now it's much better. A lot of the manufacturers are making sure their components are designed properly and don't produce PIM. So as power and voltage goes up in these devices, those electrons get pushed further into the material. You get more electrons, higher packed, and they'll want to be apart from each other, and they tend to go up into the other material. So having the plating thickness correct is important. That's just one example. So devices are getting better and better. All right, well, common sources, obviously connectors. We talk about torque, grounding straps that are improperly connected or damaged, other damaged components like antennas, diplexers, lightning arresters, damaged jumpers. As I mentioned, plating issues, poorly plated devices, ones that have poor mechanical stability. In other words, they just aren't robust enough and they move around a little bit when there's some pressure applied to them, like wind hits the hits a tower and it causes the things to move a little bit. Broken solder joints at the end of a connector or in a board inside of an antenna, and damaged connectors, all pretty common things. The bottom line is, though, why you guys care about it is because ultimately, if PIM hits your receive, it raises the noise floor. It causes the mobiles to have to transmit at a higher power to overcome that received noise. So if PIM occurs, then you end up with all kinds of problems. If you have very low PIM, you get fewer drop calls, better handoffs because the phones don't have to operate at higher powers. They have the capacity to transmit and do a handoff in low signal areas better because the noise floor is lower. The phone battery life lasts longer, so users at the edge of a cell aren't killing their battery in short order. And the coverage is operating as it was designed, so you have better coverage. As the noise floor comes up because of PIM, the actual cell shrinks. In other words, the phones have to be closer to the cell site, so because of the noise, and so you get better coverage. For LTE or data technologies, you get better capacity, better throughput, because you have better signal-to-noise ratios. So mobiles can operate with higher capacities or higher throughputs, better data rates, and so forth. And it used to be that all the technologies were voice. And voice has an awful lot of error correction in it and a lot of tolerance for higher noise floors, but data doesn't. data simply will slow down, use slower modulation schemes that are less impacted by noise. So end users will see immediately differences in noise floors. And so I was talking about this when we were first starting to talk about these higher data rate systems years ago. And I said, well, you don't experience noise on a voice call. It either works or it doesn't. But end users will see every little bit of data throughput that they lose in terms of slower response in their sites. And beyond some point, they're going to expect, at least their DSL kind of rates that they get at home. But ultimately, the bottom line is better revenue, more profit. So anyway, so let's take a look at what PIM testing is, and we'll contrast that to PIM detection. So we distinctly use the language PIM detection when we talk about our spectrum analyzers because it is different than a PIM test. So a PIM test is actually a device that injects two 20-watt tones, typically 20 watts, but they can be other amplitudes. But a typical PIM tester is going to generate two 20-watt CW signals. And those signals are injected into the device that's being tested. And any nonlinear behavior in the system results in power, right, at those other, you generate intermods, and power is then present in that intermod. And so a PIM tester simply is a power meter looking for power at that other intermod location, usually the lower intermod location. So it injects the tones, then looks for the intermod that would appear if there's a nonlinear response in the system. And so PIM is basically a linearity test. What goes in is supposed to be what comes out. And if power appears at those intermod locations, it's not linear. The response is not linear. And beyond some point, it'll be termed as nonlinear, and it doesn't pass the test. So if you look at this chart, in this example, I've got power levels here. Let's say the two carriers are being transmitted at 20 watts. And then the power is measured down at this lower frequency. Let me get my, so I can measure the power at this frequency, 846.5, which is the distance difference between these two carriers below the carrier. And that power then is deemed as the amount of PIM you have. And it's usually a relative measurement relative to the carriers. So two carriers at 20 watts would be 43 dBm. And so one metric which was used, I'm not sure what the values are nowadays, but for an existing older site in service, they would tolerate maybe 123 dBc or power below these carriers, and that would make the power level of the intermod minus 80 dBm relative to 43 dBm, and you get minus 123 dBc, or difference between the carrier and the intermod. One other thing that's good to note is that generally, if the carrier power changes by about a dB or so, that'll cause a change in the intermod. So if my carrier power goes up by 1 dB, the intermod will typically go up by 2.5 approximately, sometimes 3 dB. So the bottom line is PIM will come on very quickly and disappear quickly due to changes in the carrier power. All right, well, this term dBc, as I mentioned, PIM is often measured in terms of dBc when you're talking about a PIM test. So sample, or, you could measure absolute power, or you could measure power relative to the carrier. So as I mentioned before in that example, minus 80 dBm would be the absolute power in this intermod that's down here at 846.5, or you could reference that power level relative to the power in your carriers by saying minus 123 dBc. Often new base stations, when they get installed, they get installed at a higher standard. So often that's going to be at least minus 140 dBc. And then sometimes the standards get relaxed for existing sites because they've been in service a while and you can't expect the same kind of performance in those. But that's just a sample. It varies by carrier. Now, once a site's in service, you can't do this test, right? So PIM testing, if the site's in service or it's inaccessible, being it's a remote radio head, you can't really do this test unless you're a tower crew and you can climb the tower and drag a PIM test up to the top of it. So that's where PIM detection comes in. The primary use of PIM detection, one of the primary uses is when you don't have access to the RF connectors. And so what's PIM Detect? Well, PIM Detect is used to detect the problem with the base station's receiver. In other words, you can have PIM issues and the receiver never sees those. And I'll just share one example I have. This has probably been now 5 or 6 years ago. I was asked to go to a site for one of the major carriers, and they had a base station that was exhibiting receive problems. And they said, we want to PIM test this site and fix it. Well, it was a very difficult site because it was a flagpole site. And so the antenna space was very limited, and so they had to use, single antennas for many carriers. And there was all kinds of plumbing to get everything, jammed into a single antenna. So there was all kinds of combiners and duplexers and diplexers, and I think there was 4 different base stations all ending up in one single antenna in each sector. And it took us 3 days to go through and fix all the issues. 3 days. And, the carrier was spending, probably, I don't know, when we were all done, between the tower crew and everybody doing the testing, they were probably spending somewhere around $10,000 a day. Well, 3 days later, the base stations and the cables and antenna systems are PIM-free. Turn the radios back up, and there was absolutely no difference in the receive. So that just, I use that just to illustrate the fact that you can have PIM issues in a base station, but if those PIM intermods never hit your receive, you really don't have an issue. And why fix something that isn't impacting your receives, right? So PIM detection uses the spectrum analyzer to monitor the base station's receive and detect the presence of PIM. So that's a distinct difference between PIM testing and PIM Detect. PIM Detect will allow you to look at your receives. So instead of using CW tones, a PIM detection actually uses the base station's power and monitors the base station's receive to detect the presence of PIM. Our PIM detection feature also provides guidance and helps you configure the settings for the instrument. You can use the spectrum analyzer just all by itself if you want, and a lot of more experienced people will do that and not even use the PIM detection feature. But PIM detection just lets you go through and sort of automates and allows you in just an easier fashion to set everything up for PIM testing, or PIM detection rather. So you can do a PIM detection if you have access to an RF coupled port. So if that's a ground-based base station and you do have an RF coupled port, you can use PIM Detect. But if you don't, you can use an optical link via RF over CPRI, because you can see the receiver either way, either with an RX coupled port or looking at the receive signal coming from the radio head if it's remote on a fiber. Either one of those methods can be used with PIM Detect. And obviously, as everything goes more and more to RF over fiber, it gets a lot more difficult to access radios. PIM Detect is very useful. All right, so there are advantages, specific advantages of PIM detection. One of them is because PIM testing uses 220-watt carriers, if somebody hooks up a PIM tester to an antenna system, they will often have to put those carriers at frequencies that don't create intermods in receive paths. In other words, if they create PIM inside, you know, or they create and transmit signals that happen to fall into the signal locations of carriers and or receives, it transmits or receives, they create interference. So they're often placed, the carriers are often placed strategically so they don't interfere, which means what they're doing is actually testing at frequencies that aren't your transmit and receive frequencies. They might be close, but they're not going to be right in your receives or right in your transmits so that they don't interfere. Well, that doesn't necessarily then test your actual receive. The other advantage of PIM Detect is that it uses the power of the base station. So if your base stations are transmitting more than 40 watts, you can actually test at more than 40 watts because your base stations are being used in PIM Detect to detect PIM under potentially maximum power output levels. Remember in the slide prior I mentioned that PIM detection, or I mentioned rather PIM testing uses 220-watt carriers, or 40 total watts. Well, if you are just barely on the edge of producing PIM and the base station passes the PIM test, and then you turn up your base stations and you're transmitting much higher power levels, remember 1 dB change inside a transmit can translate to 3 or 2.5 or 3 dB on the PIM intermod. So small changes above 40 watts can produce PIM that now impact your receive that you can't see with a PIM tester. So if you're transmitting 50 watts or, you know, much higher power levels, well, you're going to produce PIM on your receive that you can't see with a PIM tester. So using the maximum power of your base station is, you know, is important if you're trying to detect PIM under actual conditions. The other thing that's nice about PIM Detect is it doesn't require multiple test sets. It really uses your radios and one spectrum analyzer, not a test set for every different frequency that you have to PIM test, like a PIM tester requires. Some PIM testers will do multiple bands, but as of now, there's not a PIM tester that will do all the bands. So you're usually stuck if you're PIM testing, getting, you know, carrying multiple boxes, you know, out to the site to make sure you can test all your frequencies. The biggest advantage, or one of the biggest advantages, is that you can use PIM Detect when you have a CIPRI radio or a remote radio that's fed with an optical fiber. Another advantage of PIM Detect is when you're doing a PIM Detect, you can actually see the noise floor, and so you can determine is it PIM or is it interference. And probably experienced, you know, doing PIM testing and having the end result be that it didn't impact the performance of the receiver because it wasn't actually PIM. So, you know, that's an expensive misdiagnosis, because if you get a tower crew out and they replace things and do PIM testing and send hardware back to, you know, because it didn't pass a PIM test when, you know, really wasn't causing a problem, well, that's an expensive proposition. Just to give you an idea, I was at a site where we connected with CIPRI, with the RF over fiber, and they had changed out everything at the site trying to get rid of what they thought was PIM. It turns out it was an external interferer that looked a little bit like PIM but wasn't. Well, they had 3 separate tower crew runs out there and swapped out everything in the sector, and I think they had estimated it was somewhere around $25,000 they'd already spent on the site, and they could have spent another $100,000 and wouldn't have fixed the problem because it wasn't part of the system. It was an external interferer. So, huge advantage of PIM detection is also that you can do this while the radios are in service. Now, if you don't have a coupled port, optical coupled port, you may have to take the site down, and Sprint does not usually have coupled ports, so you have to take the site down momentarily to connect in a coupler. But once that coupler's there, the site's back up and going. So worst case, it's going to be down for a minute or two, and then you can do everything else in service. So you're not taking a site down for hours and hours on end. So you have much higher tolerance for actually doing this even in busy hours because the site's not down for very long. The bottom line is PIM Detect you can use to determine, do we really have to get a tower crew out there, and do we need to spend all that money on a repair? All right, well, there are some advantages of PIM testing over PIM detection. And one of those is that PIM testing, remember we said that PIM testing is really a linearity test of everything that's in the antenna system. So it really does tell you the quality of the connectors and components, and so it really should still be performed, especially by construction crews, and especially if they're building any field-built kind of components like connectorizing or anything like that. Another advantage of PIM testing is that you can do, now the newer PIM testers have a distance to PIM feature typically, and if a contractor is trying to figure out where is the problem, they can utilize that to figure out where in the system the problem is, and it'll make their repairs a little bit faster. But for a technician who's just trying to decide, do I need a tower crew or not, it doesn't matter to them where the problem is. They can't get to it anyway. They just want to know, is it PIM or is it not PIM, so that they can get a tower crew to address it, or they can go after the actual issue that's the problem if it's not PIM. You can still use PIM Detect on ground-based systems. For example, if you have jumpers at the ground level, or it's a rooftop site where you have access to all the components, you can still use PIM Detect because you will see PIM on the device, and you can go do a tap test and see that result, see what happens when you stress connectors a little bit by tapping on them or applying a little bit of pressure to the connector or whatever. That will still show up on the analyzer and give you an indication of PIM. All right, so we distinguish in our CellAdvisors the difference between multi-carrier PIM and single-carrier PIM. And when we refer to multi-carrier PIM, we're typically talking about everything but LTE. So LTE would be considered a single carrier. It's really not. It's really multiple carriers inside the LTE carrier itself, but when we say multi-carrier, we're talking about, for example, CDMA or UMTS or GSM, all on the same system that can produce intermods by getting mixed and producing PIM. So in this example, what you see here is this wideband CDMA carrier is mixing with this GSM carrier, and those two produce an intermod that falls into an uplink. So those two together get mixed, and if there's a PIM issue, they get mixed, and a PIM artifact appears in an uplink. So two distinct separate carriers, multi-carrier, combining to mix and creating a PIM artifact. And again, the distance between these carriers, D, is the same distance down that you would see the artifact at, right? Just that simple formula. All right, so that's multi-carrier. Single-carrier PIM, or generally what we refer to as single-carrier PIM, is really LTE generally. And LTE is unique because in LTE you've got 50 different independent carriers in a 10 megahertz LTE carrier. If you have a 20 meg LTE carrier, there'll be 100 independent resource blocks that can pop on and off at any given time. So it just scales up with the carrier bandwidth. In this example, what I'm trying to illustrate here, and I tried to animate this and couldn't get it to work very well, so I gave up, but I'll kind of describe it here. So if you look at resource block 1, if it turns on and you've got a PIM issue, if resource block 1 turns on and resource block 50 turn on, they'll mix and create a PIM artifact down here at the very furthest point away from those two carriers. So this little artifact clear over here at the left gets produced. Now, if you look at an LTE carrier, that spot, which is the distance away from resource block 1 and resource block 50, only those two resource blocks can hit that spot. But if you move in a little closer, for example, if resource block 2 turn on and resource block 50, you'll get an intermod that appears a little bit closer to the carrier. And likewise, if resource block 1 turns on and resource block 49 turn on at the same time, you'll get another one. That's the one indicated with the green here. So as you move in closer to the carrier, as you get closer and closer, the number of different resource blocks inside the LTE carrier can hit, multiples of those resource blocks can now hit. You can, as you get closer in, you'll get a bunch of different resource blocks that can turn on and produce power as you get close in. And so what you end up with in LTE is a slanted, increasing power intermodulation distortion artifact that rises as you go in towards the carrier. You'll get artifacts on the left-hand side of the carrier that rise as you go into the carrier. And on the other side, you'll get the same thing. Further away, it'll be lower in power, and then it goes into the carrier, it grows and rises. Okay, so there's a difference in what you want to do when you look for either single carrier or multi-carrier PIM. In multi-carrier PIM, you're typically looking for rises in the noise floor, and those rises will come straight up. Whereas when you're looking for PIM artifacts inside of an LTE system, you often look for slants in the noise floor. Now, the noise floor can also rise, but it'll be slanted as well. Now, the slant is usually always the same slant, but it could be slanted and elevated. And so this is just an example of what that looks like. So you end up with these slants that end up showing up in your uplink. Now, one thing I want to mention here is that, when you look at an LTE carrier, the actual PIM artifacts may appear here, the first intermod. They'll appear over here to the left-hand side of the carrier and grow as they come in. And those don't necessarily interfere with the receive. But if these things grow large enough, if PIM is really bad and they're much higher levels, well, now all of a sudden you have mixing of this, what's called the third order intermods, will remix. So this guy here can mix with this guy. So these two signals, the original resource block, which is right here, and now this new PIM artifact, those two can mix and they'll show up down in your receive. So for most LTE systems, it's the higher order intermods that impact the receive. Now, a PIM tester might say that this failed, and you might spend a bunch of money repairing it, but if the PIM isn't bad enough, it's not going to walk down into your receive. And so that's basically what happened. That first story I shared with you is we were fixing a bunch of system components that never produced intermods high enough to remix and end up inside the receives. Even though they failed the PIM test, they never walked down and hit any of the receives. So you can spend all the money fixing the site, and yet it still can have no impact unless the PIM is really bad on, on the receive. Okay, well, here's a sample of, a PIM artifact, and you can see distinctly this rise in the noise floor from left to right. And so generally with our PIM detection, we put a marker out there on the screen, and you can move the marker around. I just want to mention a couple of other things here. You can also turn on averaging, and that'll slow down, the signal, and you can see averaging, the averaging will slow down that and allow you to see the levels a little bit more easily. You can also do things like turn on min hold and max hold. What you're really looking for is a slant. Here's another. This is a really bad example, and you can see here the slant's pretty clear. You can see it very distinctly in the max hold here at the top. But really, this slant never gets any worse. The actual signal, once the PIM was fixed, should have been down here at the bottom of the display. But what you'll notice is it slants and rises. It doesn't slant more. Usually it will slant up. If the PIM level were very low, I would just get a slant down here on the noise floor like this. But as the PIM gets worse and worse, the whole thing rises up. And that whole slanted noise floor comes up. Doesn't slant more, just gets higher. All right, so our PIM detection feature, which by the way is available inside the Spectrum Analyzer, so you'll notice here it says Mode Spectrum Analyzer at the top of this screen. And so if you were connecting to an RF port, this would be the screen you would go to. So essentially in the analyzer, you go into the Spectrum Analyzer and you hit the measurement button, and one of the measurements that's available, I think you have to hit measure then more, is PIM detection. And so you'll get this screen that will come up. And on this screen, there's an option here called Calculated PIM. And essentially, what you can do with Calculated PIM is it'll let you put in 2 different frequencies, and you can use those 2 different frequencies by entering them to see what frequencies and what level of intermod would actually hit your receive. In other words, those 2 signals may mix, and the lower level intermods, so the distance between 746, hopefully you can see that, and 756 will produce an intermod that hits at 736 and 766 right here. But as remixing occurs, you'll get intermods that appear in other places. And so you can use this screen to enter the original frequencies of your transmits and then see, does any of the mixing ever end up hitting my receive? And sure enough, if you look right down here, yes, in fact, it does. Actually, that's part of a receive band that maybe gets hit. So this is really just a calculator to allow you to determine, can my transmits ever hit my receive? So that's the calculated PIM feature. Now, when you're setting up the test, you have the option, and by the way, you'll notice there's some instructions in the PIM Detect feature that give you simple, simple instructions. It'll say, okay, well, go ahead and set things up. And in here, in the PIM Detection feature, you can set the resolution bandwidth, and generally it's recommended that if you're working on an RX port that has gain, that you set that resolution bandwidth to 10 kilohertz. If the RX port has no gain, then you would typically set that to 3 kilohertz. And you can turn on some averaging. Typically, it's recommended about 10 averages. That way you slow down. If there's any mobiles there, it'll kind of average those out, and you'll be able to see the actual PIM. And so ultimately, the PIM detection feature will take you into a screen that shows you the trace. And you can, in that trace, turn on minimum hold. Oftentimes, if there's a lot of activity on the site, it's hard to tell what's going on. Min hold is a good thing to turn on. And I would generally recommend that if this signal is crazy because you have a lot of traffic, I would turn on minimum hold. The other thing you can do is you can turn on the preamp if you don't have any gain in the RX port. You can turn on a preamp as well. And when you're taking this, if you're using multi-carrier PIM Detect, oftentimes you'll want to turn down one of the carriers. If it's a multi-carrier and you've got, let's say you've got CDMA carriers, I don't know, we'll just throw out a number. We'll say there's 4 CDMA carriers. Well, you could block 2 of those carriers to lower your power. And then that would allow you to capture a trace with the receive. And then you could turn that back up and see if there's a change. If the noise floor rises when I turn up carriers that have previously been turned down, that's PIM. I shouldn't see a change in my receive based on a change in my transmit. If you're talking about LTE, you're looking for a slant. You can't turn down part of LTE. You're stuck with the whole carrier or not. So you're going to leave that carrier on, and you're going to look for a slant. And ideally, in LTE, what you want to do is turn the power up to maximum. And for LTE, if you have access to do that, well, there's two things you can do. If you're trying to test a receive on LTE and look at a receive to see if there's PIM, if you don't have access to that, make sure you go out there when the site's busy, because you want max power, and LTE fluctuates its power transmissions based on its how many users are on the system. So if you can't take the site down, then what I'd recommend you do is go out there in a service window, put the coupler in. If it's not an RF port, if you can't get to an RF port, you have to get to the optical. Put the coupler in, install the coupler, and then come back when the site's busy. The site will be up with the coupler in there. But come back and do the testing when the site's loaded, so that you have the maximum chance of catching PIM. Now, I would encourage you to talk to the RF engineers in your markets. Engineers should have access to be able to put the base stations into max power mode. And the term is different depending on the market. So if it's an Alcatel-Lucent market, they call that OCNS. And if it's an Ericsson market, they have a different term for it, I think. But it's really, it's the same thing. So Ericsson, the AILG, will produce maximum power. Now, it doesn't take the site out of commission. It actually will still send data to users, but it sends it to all the users at max power. Yeah, now there is a downside to it. When you're transmitting at max power, that sector will create some interference in an adjacent sector. So it does have some impact, but it still doesn't kick users off the sector. So you may want to talk to your engineers at others, in your markets, and ask them if you can get them to turn it on, either OCNS or AILG. OCNS for Alcatel-Lucent and AILG for Ericsson. And I think Samsung has the same term. I think they use OCNS as their term as well. Okay, so once you can see the trace, you can make various adjustments. You know, you can put in, turn on and off the preamp and get the trace to view the way you want it. And then generally I'd recommend on a noise floor for LTE, you've got to be looking somewhere around neg 120 on an RF connection. If you're using RF over CPRI, you don't have to worry so much about the level. But if you're doing this in an RF coupled port, if you have access to those, then you're going to be wanting a noise floor to show somewhere around neg 120. Now, if you're using the PIM detection software, you can hit continue, and it'll come back up to another screen and tell you if you're doing the multi-carrier PIM detection. It'll come back up and say, well, turn up the other carriers. So if you're doing this on CDMA and you would turn down a couple carriers, then now you're going to turn them up. And once you turn those other carriers back up, it's going to take another trace. So the PIM detection feature will actually save the trace, bring up the power, and then show you the new trace. And what you see here on the left-hand side, you see how this particular screen, it's really, you know, pretty flat. There's really not a big change in the two carriers. There are the two noise floor traces there. As you know, if you have PIM, then what you're going to see is you're going to start seeing an elevation. So you can start to see, you know, the power levels are coming up on the second trace. So you'll have overlaid one trace on another, and you'll see the power levels start to come up. And generally, if that power level comes up, you know, 2 or 3 dB or more, then you've got an issue, because your actual uplink should not be impacted by your transmit. And what you'll see on LTE is typically just an increase in the slant, or the thing will be slanted and the slant will raise even between low power and max power. Okay, so here's an example of using RF over CPRI, and you can see in RF over CPRI you have the additional convenience of being able to look at both antennas by simply changing the antenna container group you're looking at. So in this example, what happened was one antenna was looked at, and that's the orange, and it was good. And then for comparison purposes, that trace was captured, and then the antenna container group was switched, and we switched to a different trace, and then we're able to capture the live trace, and that live trace shows that it's slanted. Another very convenient thing you can do is look at a spectrogram. And the spectrogram allows you to actually look at and see the same kind of thing. And again, in this case, the spectrogram was run for a period of time on one antenna, and then it was switched. And it was switched right here. And you can see the power as you go from right to left on this carrier. This is the receive of an LTE base station. The power starts to come up, and the color chart over here at the left, you can see it changes from blue and starts getting into the green and yellow. And so you can see very clearly on this spectrogram that you've got additional power on the other antenna that rises from right to left. And it's kind of hard to see on a trace sometimes, because the trace will be jumping around based on mobile traffic. But it's very clear inside the spectrogram here in the color chart up above what's going on. Now, ideally, if you don't have access to the OCNS feature, or for Ericsson AILG, I think most of your markets are going to be Alcatel-Lucent or going to be Samsung, then make sure you do this at a busy hour. And if you can't take the site down during busy hour, insert the coupler in the maintenance window and then come back during the busy hour, and you can just plug into it at that point. The base station won't be impacted at all. Now here's another example of that PIM issue, and you can see this is the slide I showed you before where you've got the PIM slant, and it was a loose connector essentially, and once that connector was tightened, it immediately dropped in power and the slant went away. So these are really the same site, just moments after the connector was torqued. All right, I'm going to go ahead and stop there and in the WebEx here, and feel free to give us a call at any time. Thank you for attending, and if you have any other questions, don't hesitate to give us a call.